gardening expert Peter Seabrook offers some seasonal advice on Christmas presents for gardeners. Here on BBC2, our daytime programmes continue now with a look at graphs in Maths Help.
Problem 1. Complete this table of values for y. 2. Using a scale of 1 centimetre to represent 1 unit on the x-axis and 1 centimetre to represent 5 units on the y-axis, draw the graph of y equals minus x squared plus 5x plus 6 for values of x between minus 2 and 5 inclusive.
That looks a really tough trip. Look at all the words. It overwhelms you with information. But don't panic. The questions with the most words often turn out to be the easiest in the long run. So, what do we know? We know something about graphs. You can't avoid seeing graphs if you look at the newspapers or the television. They're used to connect quantities such as unemployment and time, or sometimes dollars and pounds. There's always two lines, a vertical one and a horizontal one. And then the graph is a picture on that showing the connection between the two quantities. So in fact, they are quite familiar, although that problem we started with may have looked rather forbidding. So, I'm going to be taken for a ride. This is easy. All I have to do is to sit here. This particular taxi charges me £1, whatever the journey, and then it's 50p per mile after that. So on we go. That was a quick mile. And I owe the man £1 for getting in and 50p for that mile, £1.50. Let's record that information. The distance, 1 mile, the cost, £1.50. On for our second mile. That was exceeding the speed limit. 2 miles, £1 plus 2 lots of 50, that's £2. Let's enter that one up. 2 miles, £2. On again. This is faster than sound. 3 miles. That's £1 plus 3 lots of 50, that makes £2.50. Enter it up. And obviously, for 4 miles, it's going to be £3, and so on. The first way of describing the cost of this taxi ride is this table we've just made. It is incomplete. It only tells me the cost of certain rides. But if you were just given that table without explanation, a pattern would show in the numbers. The second way shows that pattern visually, and it leads us to a graph. Draw 2 axes, as in all those graphs we saw. Mark the horizontal one in miles, the vertical one in pounds. Now we can store the information from the table in a different way. For 1 mile, the cost is £1.50, so we mark this point. For 2 miles, the cost is £2, the point is here. Then for 3 miles, £2.50, and for 4 miles, £3. We've now stored exactly the same information. It is tempting, and I never resist temptation, to join these points up to make a straight line. But yield to temptation with caution. By drawing that line, we've got a lot of extra points. Do these other points on the line mean anything? Take a distance of 2.5 miles. Go up to the graph and then across to the cost axis. It says £2.25. Is that right?
It depends.
If the meter ticks over smoothly, the way a petrol pump does, then it is right. If, on the other hand, it goes in 50p jumps, and that is the way a taxi normally does, then it is not right. We need to check the information back with the real-life situation. Let us be tempted again. Let's extend the graph. First, out to the right. When it hits an exact number of miles, it seems to work. 5 miles would give £3.50. What about 30 miles or 3,000 miles? Hang on. The mathematics may be all right, but no way is that taxi driver going to take me 3,000 miles. Beyond a certain number of miles, which the taxi driver decides, he will want to negotiate. Now, let's extend it back to see what happens there. 0 miles is going to cost me £1. He's going to agree to that. What does it mean when the line goes right back through the axis? Is he going to reverse back 2 miles and charge me nothing? Crazy. That graph expresses a relationship between two mathematical quantities, but it does not know the mind of the taxi driver. It stores up more information, but we need to know if it's sensible information. So what we've done is set up a mathematical relationship that derives from a real-life situation. So leaving our reality behind, we'll move off into our mathematical world. Because if we're going to solve this problem, we need to know a bit of maths. Now this graph here contains all the information. The real-life part is just a few points in this area here. So, on the one hand, mathematics has great power. On the other hand, you need to use your common sense to check it out. Now, there is a third way of looking at this situation. We can express things in terms of a simple English sentence. To find the cost in pounds, you multiply the number of miles by a half and then add 1. Half because it's 50p, or half a pound for every mile. 1 because of the £1 initial charge. This English sentence is as all-embracing as the graph. It will make it easier if we change into mathematical symbols. We always call the vertical axis y and the horizontal axis x. So put the cost as y pounds and the distance as x miles. Take the sentence straight over into algebra and we get y equals a half x plus 1. So now we have the table and the graph, and we have a new thing. We have the equation. The equation is as powerful as the graph. It contains a great deal of information, and as before, the mathematics needs to be checked back, tested against reality. Here is our problem again. That is our table, and if we look down the left-hand side, we can see that the equation we must have been using is y equals minus x squared plus 5x plus 6. The table has been left incomplete. This time we have an equation, and if we complete this table, then we should be able to draw the graph. So that means that we have to do some arithmetic, we have to draw the graph carefully, and then all should be well. The table then. The examiner's helped us out a bit. Nice of him. Work through the first column to see what he does. If x equals minus 2, then x squared equals plus 4. Remember? And minus x squared is minus 4. Then 5x is minus 10. So his column is right, and he can also do sums. Watch us do some. There we are, the table is complete, and we have some marks. And all we've done is some arithmetic. Now, to get this information on a graph, we need 2 axes. The scale is 1 centimetre for 1 unit on the x-axis, and 1 centimetre for 5 units on the y-axis. So let's plot the points one by one. We have x is minus 2 and y equals minus 8, giving this point. Minus 1, 0 gives us a point on the x-axis. 0, 6 is on the y-axis. 110, 212, 312, 410, and finally 5, 6. Now, when we do join up these points to get the whole of the mass, as it were, we certainly can't draw a straight line as we could with a taxi. Well, we must do the best we can. There's an inbuilt smoothness to these points that tempts us to draw a curve through them like this. Very elegant. It's not too easy to draw a smooth curve, and you'll need to practice. But we are there. We have the graph, the equation, and we have the table. We have linked the three together, and we have scored our marks. Now, have a look at this graph, this nice symmetrical form here. This is called a quadratic. It's called a quadratic because the word quadrate means to make square, and there's an x squared in the equation. It also has one single bend. If we had a cubic, there would be two bends in the graph. Now, will a quadratic ever appear in the real world? Well, back in the Middle Ages, they got quite interested in dropping cannonballs on each other's heads. And it was Galileo who first discovered that the path of such a missile was, guess what?